Welcome to this explainer. As a materials scientist, I am just incredibly excited to show you how diamonds are finally stepping out of the jewelry box to completely replace silicon in our modern technology. We usually think of diamonds purely as these glittering status symbols, right? Carefully cut to sit on a ring. But hidden inside their crystalline structure is a massive, untapped power that is literally about to revolutionize every single device you own. We are standing right on the brink of what many of us in the field are calling the new diamond age.
Okay, let's dive into our agenda for today. We'll be covering 1. The limits of silicon. 2. Why diamonds outperform silicon. 3. Forging synthetic superdiamonds. 4. Powering future consumer devices. And 5. Simulating extreme planetary pressures. We are going to track a fascinating journey from the thermal limits of your overheating laptop all the way to the search for extraterrestrial life. We'll explore the molecular magic of diamonds and see how scientists are now literally outperforming billions of years of geological evolution in just a few days inside a lab.
Section 1. The limits of silicon. The 50-year reign hits a wall. Let's start with the device you are likely using right now. It's powered by silicon. Now, this is a material that has completely ruled electronics for 50 years, but it's hitting a massive heat-induced wall. Silicon has been the undisputed king of the semiconductor industry. It's cheap, it's abundant, and it reliably transmits electricity. But as our tech gets smaller, faster, and way more demanding, silicon is exposing its greatest weakness, which is heat. The more electricity you push through a silicon chip, the hotter it gets. And that brings us to a hard physical limit.
So the absolutely crucial point here is that if a silicon chip reaches about 300 degrees Fahrenheit from the electricity it carries, it just shuts down entirely. It's essentially dead in the water. This is exactly why your laptop sometimes sounds like a jet engine trying to take off, and why major manufacturers are desperately trying to figure out how to siphon heat away from their electronic systems. Our modern technological progress is literally being throttled by the temperature of silicon.
Now, if we compare silicon to diamond, the sheer dominance of diamond is just staggering. It transfers heat so perfectly that it could run a computer at speeds that would literally melt a traditional silicon chip. Look at these numbers. Diamonds can survive environments up to 1800 degrees Fahrenheit. If we replace silicon components with diamond, we're talking about devices carrying 30 times more power and operating 3 times faster. And the best part? We can do all of that without relying on those bulky metal heat sinks that weigh down our current electronics.
Section 2. Why diamonds outperform silicon, the ultimate material. Let's see how this all builds by examining the molecular properties that make diamond the ultimate supermaterial. Because it's really not just about looking pretty. It's all about atomic perfection.
When we look at the basic carbon lattice, it becomes crystal clear why diamonds are so special. They are the hardest, most heat-conductive mineral on the entire planet. They're actually 4 times harder than anything else found on Earth, and they are completely impervious to corrosion. But the real kicker for the electronics industry is this. While pure white diamonds are perfect electrical insulators, meaning they block electricity entirely, nature occasionally throws us a wild card that turns them into perfect semiconductors.
So pure white diamonds block electricity, right? But adding just a tiny dash of boron, like we see in the famous Hope diamond, turns the stone into a brilliant blue electrical semiconductor. It's absolutely wild. Now, the Hope diamond is famously known for its so-called curse and for glowing a blood-red color under ultraviolet light, which is actually caused by nitrogen interacting with the boron. But to a materials scientist like me, its true value is its ability to allow an electrical current to pass through it effortlessly. Those boron atoms interact with the carbon lattice to create the ultimate semiconducting material.
Section 3. Forging synthetic superdiamonds, outperforming nature. The catch is that natural blue diamonds are incredibly rare and highly prone to fracturing. So, to build the future, science had to do the unnatural and forge a synthetic superdiamond. Relying on nature just isn't going to work for the tech industry. Blue diamonds make up less than 1 in 100,000 stones. Plus, even the most perfect natural diamonds have microscopic flaws and cleavage planes. Those are basically directions where the molecular bonds are weak and prone to splitting. For our devices, we need something tougher, much larger, and available on demand.
To put the scale of this innovation into perspective, just think about the timeline of carbon. We are literally taking a geological process that required a dying star in billions of years and recreating it in a lab in merely 4 days. It's mind-blowing. The carbon in our bodies and in diamonds was forged in the cores of dying red giant stars. Those stars eventually went supernova, scattering carbon across the universe. It clumped together, formed our planet, and then sat 100 miles underground, being crushed at 2,700 degrees Fahrenheit. And today, we can literally grow a diamond molecule by molecule over a long weekend. But the big question was, how do we make them even tougher than natural stones?
Well, we found a critical clue out in space, specifically in carbonado. These are black diamonds brought to Earth via meteorites, and they taught us that the vacuum of space, not intense crushing pressure, could create a tougher, multi-crystal diamond. This was a massive paradigm shift in my field. We always assumed massive pressure was the only way to make a diamond. But these strange, porous space diamonds were made of millions of tiny crystals all linked together in a low-pressure vacuum. Because it's multicrystalline, it doesn't have those natural weak points or cleavage planes that a regular diamond does, so it's almost impossible to shatter.
That cosmic discovery was a total game changer. It led directly to chemical vapor deposition, or CVD. This is a technique that finally allowed us to legitimize the growth of large diamond wafers for industrial use. By mimicking the vacuum of space, instead of the crushing pressure of the Earth's mantle, we can essentially trick carbon into settling into its most stable configuration, which is diamond.
I absolutely love this process. It's basically a high-tech recipe. We put tiny diamond seeds in a vacuum chamber, pump in methane and hydrogen gas, and then blast those gases with microwaves. This creates a highly energetic carbon cloud that slowly settles onto the seeds, growing a perfect diamond wafer molecule by molecule. It's kind of like shaking salt onto a table, but instead, we're growing a seamless mesh of perfect diamond crystals that can be scaled up to 8 inches wide and cut into whatever shape the tech industry desires.
Section 4. Powering future consumer devices. The Diamond Age. Okay, so we've solved the manufacturing problem, but how does this chemical breakthrough actually get into your pocket? Let's explore how these synthetic wafers are going to power our future consumer devices.
When it comes to heat conduction speed, the jump is massive. Synthetic diamond plates conduct heat up to 5 times faster than the copper that's currently struggling to cool down your electronics. If you coat electronics with diamond or use diamond heat sinks, that nasty thermal bottleneck that has plagued silicon for decades, it completely vanishes. We can finally crank up the power without melting our devices. 100 billion. That is the staggering number of times per second a tiny diamond nanoresonator can vibrate. This promises incredibly robust electronics and crystal clear cell phone reception. We are talking about components 1,000 times smaller than a human hair, vibrating at speeds that completely boggle the mind, yet they remain as tough as nails because, well, they are made of diamond. This means battlefield communications that never fail and consumer tech that practically never degrades.
So what does this transition mean for us? It means our daily consumer tech will become vastly smaller, much faster, and way more efficient. Plus, diamond's perfect optical clarity will literally give NASA clearer windows to the stars. Because diamond is uniquely transparent across a massive spectrum of light, from ultraviolet all the way to infrared, it doesn't just process electricity beautifully, it processes light beautifully too. It is quite literally the ultimate building material for our future.
Section 5. Simulating extreme planetary pressures. Extreme science. Speaking of the stars, let's see how these superdiamonds are pushing the absolute boundaries of extreme astrobiology. Because it's not just about building a better iPhone, right? It's about pushing the very limits of human knowledge.
Is there life in outer space? I know, it might seem like a sudden leap from your cell phone, but synthetic diamonds are the exact tools scientists are using right now to answer this profound cosmic mystery. To figure out if life can survive on other planets, we have to recreate the insane pressures of those alien worlds right here on Earth.
Enter the diamond anvil cell. By growing a CVD superdiamond that's 50% stronger than the Hope diamond, researchers built a device that can safely simulate the crushing pressures found deep inside planetary cores. We are talking nearly 20 million pounds per square inch. Natural diamonds would just shatter into dust under those forces. But these lab-grown superdiamonds can take the punishment, allowing researchers at places like the Carnegie Institution to squeeze materials and literally observe the impossible. When scientists looked at bacteria survival, the results were incredible. They placed E. coli bacteria inside the anvil and cranked up the pressure until the liquid inside actually turned to dense ice. And guess what? 1% miraculously survived. This proves that life could potentially exist in incredibly harsh extraterrestrial environments. If bacteria can survive in environments squeezed by diamond tips at millions of pounds of pressure, who's to say life isn't hiding deep within the icy moons of Jupiter or Saturn? And we only know this because we figured out how to engineer a better diamond.
There's a great quote that says, "The synthetic diamond that will give us knowledge like steel, transistors, and silicon, welcome to the age of superdiamonds." That perfectly captures our journey in this explainer. We are fundamentally shifting diamonds away from being mere shiny trinkets and repositioning them as the ultimate utilitarian supermaterial.
They're absolutely going to give us the same kind of civilizational leap forward that steel and silicon gave our ancestors.
The silicon era is hitting a very real physical wall. So, next time your laptop starts overheating, ask yourself, are you ready for the technology in your hands to be replaced by diamonds? Thank you so much for joining me on this deep dive into the molecular future of our world. Stay curious and keep looking forward.